Hello everyone, this is, welcome to video 8.5. We're going to be looking at greatest common factor and least common multiples. Uh, we're going to go through a couple of examples of each and show you a couple of different techniques for each. This is sort of a culminating idea to a lot of what we've been looking at in the previous videos. So divisibility rules into primes into this. So if you're not entirely sure of some ideas from the previous videos, you might go back, rewatch them, or ask questions, ask me, ask people in your group, whatever you need to do to make sure you have the sort of the requisite ideas before you get too far into this video. Anyway, so let's get started. So greatest common factor. Let's sort of break down what this says. All right. So greatest. We want the biggest one. That's what greatest means. So we want the largest possible one. Now, there might be more than one common factor. In a lot of cases, there will be more than one common factor, but we want the biggest one. Common, typically, we're going to be given these where we're finding the greatest common factor of two numbers. It's possible to do these with three or more numbers. We're not going to do that in this class. You may see those problems, but we're just not going to be tackling those in this class. So we're going to have two numbers. It needs to be something that works for both numbers. It can't just work for one and not the other. So it's got to be both. And then lastly, a factor. And what we mean by a factor, we've talked about this before, is that it's a divisor, right? So we want to find the largest divisor that is common to both numbers that we're given for the problem. Now, I want you to remember there's always an answer, right? So these problems, these GCF problems, always have an answer. By the way, you'll see these sometimes as GCD, greatest common divisor. A factor and a divisor are the same thing. So a greatest common factor and a greatest common divisor is the same thing. It's just which term you want to use for whether you use factor or divisor. Uh, anyway, so there's always an answer. All right, every pair of numbers at least has one as a common factor. And if it's the only common factor, then it's the greatest common factor. So there's always an answer of at least one. In a lot of cases, it'll be something greater than one, but there are going to be cases where the greatest common factor is just simply one. So let's look at a problem sort of by the brute force method. And so the brute force method is going to be, we're just going to list out all the factors. So for 16, we know it's divisible by 1, by 2, by 4, by 8, by 16. So those are all my factors of 16. And for 24, I got 1, 2, 3, 4, 6, 8, 12, and 24. So of the GCF part, GCF, we've done the F part. We've listed out all the factors, right? The next step is going to be to look at the common, what's in common. So we can see there's a 1 in common, there's a 2 in common, there's a 4 in common, there's an 8 in common. So this is my C part done. I've got all the common factors. So now the G, I just want the biggest one. And that's the 8. So the greatest common factor for 16 and 24 would be 8. 8 is the largest number that divides into both 16 and 24. It's a factor, divides into both. It's common, divides into both. And it's the largest one. 1, 2, and 4 are common factors. 8 is the greatest common factor. Right? So this is a way that I like to introduce this idea because you get to see all three of these parts sort of working. You can see why 8 is a factor, you can see why 8 is a common factor, and you see why 8 is the greatest common factor. Let's introduce the least common multiple, and it works very similarly. So we're going to look at all three parts of this name and understand what it's asking. So now we're looking for the least. So we want the smallest one. Common still means common. Now, multiple means that both of the numbers that were given should divide into our answer. we're looking for multiples of both numbers. Now, if you remember from before, when we talked about this, the set of factors is always finite. So if I'm given two numbers, I can list out all the possible factors. That's, we know it's feasible. We know it's possible because it's a finite set. But if you remember back when we talked about this before, multiples were an infinite set. They're going to keep going. So whereas we can list out all the factors, we can't list out all the multiples. But there's always an answer because the product is always a common multiple. So if I'm given two numbers, I can always find the least common multiple, or I can always find a common multiple by just multiplying them together. So I know that if I'm given, say, 3 and 7, I know 21 is a common multiple because it's, well, 3 divides in and 7 divides in because it's the product of 3 and 7. So I could always find a common multiple. Now, whether or not that common multiple is the least common multiple, that's a different question. That's going to take a little bit of work to sort of figure out if that's the case or not. So let's go through our brute force method and find the least common multiple for 16 and 24. So, we're going to do this not by listing out all of them, but we're going to list out a few of them and see what happens. So we've got 16. 16 times 2 is 32. 16 times 3 is 48. 16 times 4 is 64. 16 times 5 makes 80. And I'm going to stop there, and we'll see if we need more past that. 24 times 1 is 24. 24 times 2, my goodness, is 48. And I can stop. So I have found here, so it's a multiple because 16 divides into 48 and 24 divides into 48. So we know these are both multiples. They're common. It's a common multiple. So it's a multiple of both numbers, and it's the smallest one. Now, I know there's at least another one coming up, because if I were to double both of these, then I would get 96 and 96, and so I would know that these would be common multiples also. And in fact, if I take multiples of this common multiple, I know that down the road, 480 is going to be down here, and we know that's a common multiple. But I only want the smallest one. I want the least common multiple. So to check to make sure that it is least, I just got to look at the numbers that are smaller than the 48 and see if I somehow missed one. 32 works here, but not for 24. 24 works here, but not for 16. 16 works here, but it's too small to work for 24. So I know 48 is the least common multiple. Again, this brute force method allows us to sort of see the mechanism at work. But for larger cases, and I picked the 16 and 24 because they're not too unwieldy to do using this method. If I have two numbers at random, these brute force methods are not really going to be very useful. So we're going to want more systematic ways of approaching this. But like I said, I like using these to introduce it because we kind of see all the pieces at work. So we're going to look at two sort of algorithmic, systematic ways of doing this. One that's in the book, one that's not. And so this slide method is given in the book. I'm not going to lie, I had never seen this before until I used this book. I think it's actually a pretty neat little method. So I like it quite a bit. I'll show you a second method here on the next slide. And then, you can choose whichever one that you like, whichever one makes the most sense to you, and use that method. So here's how the slide method works. I'm going to take my 16 and my 24, and I'm going to write them next to each other. And I'm going to put a little line here going down the left side. And what I want to do is I want to find numbers that will divide into both. So obviously these are both even, so they're both divisible by 2. So I'm going to put a 2 over here. And then 2 divides into 16, leaves an 8. 2 divides into 24, leaves a 12. So I'm going to do the same process again. So what will divide into the 8 and the 12? Well, a 2 will go in again. That leaves a 4. A 2 will go in. That leaves a 6. We do it one more time. 2 goes in again. That leaves a 2. This leaves a 3. Now, is there anything that will divide into 2 and 3? Well, the answer is no. And so there's actually a name for this, that when you have two numbers that don't share a factor, we call them relatively prime. Now, in this case, they're both actually prime, 2 and 3. So anytime the numbers are both prime, they're also going to be relatively prime. But you can have two numbers that are not prime that are relatively prime. For example, 8 and 9 are relatively prime, even though neither one is a prime. They just don't share any factors in common. 8 is only made up of 2's, and 9 is only made up of 3's. So it doesn't mean that the numbers are prime, it just means they don't share any factors in common. They are prime relative to each other. Anyway, so once we get down to this case where there's nothing else they have in common, we're going to stop, right? And now your answer is right here. The numbers along this side are your GCF. This is your greatest common factor here. So 2 times 2 times 2 is 8, and that's our greatest common factor. This should make sense because what we're constructing here on the side is the prime factorization for my GCF. I'm looking for factors in common. I'm dividing out things that will divide into both 16 and 24, 8 and 12. So I'm taking out factors that are in common. After I've taken them all out, then that has to be the greatest common factors. I've taken all of them out that are possible. Now, if I take, and let me switch to blue here. If I take all of these numbers, what's on the side plus what was not able to be factored out any further, these two numbers at the bottom, this is my LCM. So my least common multiple is going to be 2 times 2 times 2 times 2 times 3. So these are the 2's from the side. This is the 2 and the 3 from the bottom. And so in this case, we get 8 times 6 is 48. So you can see this is consistent with what we saw using the brute force methods. I can explain the GCF relatively easily and quickly. The LCM, it takes a little bit more work to explain, so I'm not going to do it in the video. If you want me to sort of like explain in a little bit more detail why this works for the LCM, you talk to me after class or during office hours. It's not too horrible. I mean, you can kind of see here that the 16 is the 2's here, and the 24 would be these 2's and the 3. So if you can kind of separate these things out a little bit, and the next slide, the next method will help make sense of this a little bit more as well. You can kind of see, but if you want to hear why this works in more detail, just catch me after class. So the second method, which is not in the book, uses the prime factorizations and uses a Venn diagram, which you may or may not have seen before. So if you're familiar with Venn diagrams, then this won't be too far afield for you. If you haven't, then you may want to skip over this method. So this is, again, not in the book, so it's largely, it's not largely, it's optional. So let's find our prime factorizations for 16 and for 24. This is 4 and 4, this is 2 and 2, this is 2 and 2. So there's my prime factorization for 16. For 24, that's 3 times 8, that's 4 times 2, that's 2 and 2. So here's my prime factorizations. So what I'm going to do is I'm going to draw my Venn diagram. I'm going to draw my two circles. And so this is my 16 and this is my 24. I want to find what they have in common, because that's going to go in the middle. And so I can see they both have a 2. They both have a 2. They both have a 2. Now the 16 has a 2 left over, and the 24 has the 3 left over. You can probably recognize this is not that much different than what we did in the previous method. We've got the 2, 2, 2 that's in common, so that's my greatest common factor of 8 right there. And then if I take all of this together, I get my LCM. So 2 times 2 times 2 times 2 times 3. So there's my 48 of my LCM. I think this shows the LCM a little bit clearer here because all the things in this circle, my 2 to the 4th power makes my 16. My 2 to the 3rd times 3 makes my 24. So you can see that this circle times 3, this circle times 2, that makes our 48. Again, I can go into more detail outside of class if you need to. But once I've constructed this diagram and I have the factors that are in common, and I know the factors that are not in common, then my GCF and my LCM are right there. They're pretty straightforward to tell where they are. You have to go through the extra work of doing the prime factorization, but once you have it, filling in this diagram is pretty straightforward. Again, this is a matter of preference. It's a matter of taste, whether you like this method or the slide method from before. Either way works. So for your checkpoint, I want you to try to find the GCF and the LCM of 2700 and 3780. Now, if you remember your divisibility rules, you can already tell some factors that these numbers have in common right away, just by inspection, by looking at the numbers. So use either method you want. I would even recommend maybe using both methods to see which one makes the most sense to you. If they're both new to you, try them both out and see which one sort of works. You should get the same answer either way, so that shouldn't be a factor. That's a little pun there. So yes, so have a look at these two numbers, 2700 and 3780. Find the GCF and the LCM. As always, if you have any questions, by all means, please let me know. All right, thank you.